Okay, this is Chapter 10, Redox Lesson 2, and today we are going to review how to assign oxidation numbers to elements in a compound or in an ion. There are specific rules that will help us in assigning oxidation numbers, and they're pretty straightforward, and usually after you've done a couple of problems, you already know them. It's not something that you actually have to sit there and memorize. It just becomes second nature. So the first rule, and the most important rule, is uncombined elements not bonded to another element have an oxidation number of 0. This includes any formula that has only one chemical symbol in it, meaning single elements and diatomic elements. So we're talking about Brinkelhoff here, Brinclhof. So some examples are aluminum solid, if it's by itself, would get assigned a 0. Na solid by itself would get assigned a 0. Br2, which is a liquid at standard temperature, would get assigned a 0. And H2, which is a gas, would be assigned a 0. So any element by itself, uncombined with another element, including Brinkelhoff, get assigned a 0. In compounds, the sum of the oxidation numbers, I'm just going to put the number sign, numbers, and what I mean by this, charges, for all elements must add up to 0. And I'm going to show you how this works right now. So we have NaCl, and in NaCl we have one Na, and it has a charge of +1. I get that from the periodic table, and we know that the sum of the charges between Na and Cl have to add up to 0. Cl has a -1 charge, and there's only one of them, so that's a -1, a +1, and a -1 is 0. In Mg3N2, this 2 came from Mg. If we look up Mg, it's got a +2 charge, and there's 3 of them here, so we have 3 times +2, which is going to equal a +6. This 3 came from the nitrogen. If we look up nitrogen, it has a -3 charge. There's 2 of them here. So 2 times -3 equals a -6, and that sums up to 0. In the last one, we know that oxygen has a -2 charge. So there's 3 oxygens times -2. That gives me a -6. That means that H and N must add up to +6. We know that H has a +1. Now you might ask why I'm not doing nitrogen next, and that's because if you look at nitrogen on the periodic table, it has multiple oxidation states, so we're not sure which one we're going to use here. Oxygen only has one oxidation state, hydrogen has only one oxidation state. There's one hydrogen with a +1 charge, which gives us a +1. So in order for this to equal 0, we know that nitrogen must be +5. So there's 1, and that's times +5. So then we add up to 0. The oxidation number is the number inside the parentheses when we were looking at these. It is the charge on one atom of that element. There is a trick. If you're dealing with polyatomic ions together, use the charge from the polyatomic ion found in Table E to determine the oxidation numbers for those elements. And remember that we must always write the negative element last. There is one exception to that rule, which I'll go over in a minute, and the positive element first in a compound formula. So for example, in HCl, my negative element is Cl, my positive element is H. In H2SO4, here you have a polyatomic. Now there's two ways you can figure this out. I'm going to show you both ways. Oxygen is -2. 2 times 4 is -8. Remember, this has got to equal 0. Hydrogen, we know, can only be +1. There's 2 of them, so that's 1 times 2 is +2. So in order for this to equal 0, then sulfur must be +6. So that's one way to figure it out. The other way they're saying to figure it out is that if you just take out the polyatomic ion, SO4 -2, now you're dealing with an ion. So this is going to be -2, which is -8. And here, because it's an ion, it doesn't equal 0. It equals the charge on the ion, which is -2, which would mean that this would have to be +6. So you could do it that way, and then you know hydrogen had to be +1. Okay? That's just another way of doing it. I think it's fine just to do it all together like I did in the middle example. There is one exception to the rule, NH3, in which case the -3 is written first and the +1 is written second. This is the only exception that you have to worry about. Let's move on to Rule 3. Group 1 metals always have a +1 oxidation state. If you look down all your group 1 elements, in the upper right hand corner you see a +1. And group 2 metals always have a +2 oxidation number when located within a compound. Here's an example. Lithium's a group 1, so this is -1, this is +1. I didn't have to do any work there. Here's a group 2 metal. Chlorine is -1. -1 times 2 is -2. This has to equal 0, so Mg had to be +2. Rule 4. Now we have a couple of exceptions coming up. Rule 4 is an exception, and Rule 5 is an exception. And actually Rule 6, but I'll wait till we get there. So these are some exceptions coming up. So fluorine is always a -1 in compounds. The other halogens, ClBr and I, are also -1, so long as they are the most electronegative element in the compound. So here, fluorine's -1, hydrogen's +1. Here, chlorine's -1 times 2 is -2. Therefore, calcium is +2. And we know calcium's +2 because it's a group 2 element. Br is -1. Na is +1. So all of these examples were cases in which halogens were -1 because they were the most electronegative element in the compound. Rule 5. Hydrogen is a +1 in compounds unless it is combined with a group 1 or group 2 metal, in which case it is -1. Examples here, this is chlorine's -1, so hydrogen's +1. Notice here lithium's a group 1 metal. In this case, the metal is +1 and the hydrogen is -1. This would be called lithium hydride. So whenever you have a metal plus H, H is -1, and it forms what's called a metal hydride. So that's the first exception there, or second exception. And oxygen is -2 in compounds. Put in the word usually, because there is an exception. Is usually -2 in compounds. So here, oxygen is -2, that gives me a -2, it has to equal 0. Hydrogen has got to be +2, but there's 2 of them, so 2 divided by 2 is +1, so each hydrogen is +1. When it is combined with fluorine, F, which is more electronegative, oxygen is +2. So that actually goes back to that rule. Fluorine and all our halogens are -1, okay, unless they're combined, as long as they're the most electronegative element. So fluorine and oxygen are both part of Brinkelhoff. They would both be negative, okay, except for fluorine has a higher electronegativity. So now in this case, oxygen's got to assume the positive charge. So here fluorine is -1. -1 times 2 is -2. So in order for this to be equal to 0, oxygen has to be +2. When in a peroxide, oxygen is -1. So oxygen's got 2 exceptions. Oxygen is -2 unless it combines with fluorine, and if it forms a peroxide, oxygen is -1. A peroxide is a compound that has a general formula of X2O2, where X being some other element. So let's take a look at a couple. Here we see this general formula, Na2O2, so we know that this is the peroxide ion. So here oxygen is -1, that gives me -2. This has to be equal to 0, this has to be +2, 2 divided by 2 is +1. In this one, same kind of general formula, H2O2, O2 is -1, that gives me -2, this to be equal to 0, this is +2, 2 divided by 2 is +1. And the last rule, the sum of the oxidation numbers in polyatomic ions, so now we have an ion, must equal the charge on the ion, and that can be found in table E. So in this case, I'll do one example. You have Cr2O7 -2. Now I'm going to show you both ways. Over here we know oxygen is -2. -2 times 7 is -14. Therefore, this now equals -2 because it's an ion, not 0. So in order to get a net -2 and I have a -14, this must be a +12 for the CR total, because a +12 and a -14 is -2. But notice I have 2 CRs, so 12 divided by 2 means each one is +6. Doing it over here, I have 7 times -2, which is -14. The charge on the ion is -2, so that means that this has to be +12, and there's 2 of them, so 2 times +6 is +12. A reaction is redox if oxidation numbers change for 2 elements in a reaction. Remember, reduction is gain of electrons by an atom or ion. The oxidation number goes down, and I like to put in here becomes more negative, and we call this reduces. it reduces. We actually learned this in the first lesson. Oxidation is loss of electrons by an atom or ion, and the oxidation number goes up. So we say this becomes more positive because you now have more protons than electrons, and it oxidizes. So let's look at a couple examples. The first thing that you want to do to determine if something is a redox reaction, meaning you have oxidation and reduction occurring simultaneously due to the loss of electrons by one species and the gain of electrons by another species, is you need to assign oxidation numbers for all elements in the reaction. So we know that C is by itself. Anything by itself gets assigned a 0. We know that oxygen is always -2 unless combined with fluorine or in a peroxide. So this gives me a net -2. If the whole thing has to be 0, then this has to be +2, and there's 2 of them, so hydrogen has to be +1. Oxygen is -2, which means carbon has to be +2, and H2 is by itself. It's a Brinkelhoff, so it gets assigned a 0. Now, the only thing that we're interested in looking at are the top numbers, okay? We look at the oxidation numbers to determine whether or not something's oxidized or reduced. Anything that we do below the reaction is just helping us do math to determine the oxidation numbers, and we're not interested in them. So C0 is going from C0 to C +2. So the charge is doing what? Increasing or decreasing? Well, it's going from 0 to +2, so it's increasing. And when it increases, becomes more positive, which is what it's doing, it's losing electrons. So it lost electrons, and it is oxidized. H+1, which is right here in H2O, goes to H0. So my oxidation number is decreasing. And if it's decreasing, that means that it's becoming more negative. So that means that it gained electrons, because when you gain negative charge, you become more negative, and that means it is reduced. Let's do one more example. Example 2. So starting with oxygen, oxygen is -2 times 2 is -4. In order for this to equal 0, then Mn must be +4. Cl is -1, H is +1. We don't worry about this 4 right now. We're just looking at the compound to assign oxidation numbers. Cl is -1 times 2 is -2. In order for this to be equal to 0, Mn must be +2. Cl2 is by itself. It gets assigned a 0. Oxygen is -2. There's only 1, so that's -2, which means hydrogen has to be +2. 2 divided by 2 is +1, so each hydrogen is going to be +1. Water will always be +1, -2, respectively, for the elements that are in the compound. So let's see what's going on. We have chlorine going from -2 in -1 in HCl to 0. So I'm going from -1 to 0, so therefore my oxidation number is increasing. It's becoming more positive. And when it becomes more positive, it means that I lost electrons, and that is oxidation. Leo. Loss of electrons is oxidation, and the oxidation number becomes more positive. Mn +4 in the MnO2 changes to Mn +2 in the MnCl2, so my oxidation number is decreasing, and when it decreases, it's because I'm gained electrons, because when I gain negative charge, it becomes more negative, and gain of electrons, is reduction, so it is reduced. Now, the last thing that I'm going to talk about today, and this is just something you have to remember, is backwards. The oxidizing agent is the species, that is reduced. It is the species that does the oxidizing. And I know that that sounds really weird because I'm saying that the oxidizing agent is the species that is reduced. When I refer to species, I'm referring about the compound. The reducing agent is the species that is oxidized. In other words, it is the species that does the reducing. So note that the oxidizing agent and the reducing agent are always located on the reactant side of the equation, and this would be the left side. So assign oxidation numbers for all elements and identify the oxidizing agent and the reducing agent. So C is by itself at 0. We said water is always +1, -2. Oxygen is -2. That makes carbon +2. And H2 is by itself, it's 0. So carbon is going from 0 to +2. It's becoming more positive, so it's losing electrons and it's being oxidized. So the species that is oxidized is called the reducing agent. So this would be C0. So you just basically have to remember that the species that's oxidized is the reducing agent, and the species that is reduced is the oxidizing agent. We have oxygen is not changing at all, so we're not interested in that, but the hydrogen is going from +1 to 0. It's becoming more negative, which means it's gaining electrons. It was reduced and therefore is the oxidizing agent. So we list the whole compound. Water is the oxidizing agent in this case because it contains the hydrogen. Okay, that's it for lesson 2. We'll see you next time for lesson 3. Have a great day.